in this video, I want to recap the explanation from lecture about Shaq's success rates in different games. Okay, so here's the basic question that we're trying to answer. So let's say that this is the small data set that we have. So we have like game 40, 41, 42, 43, whatever. And let's say that in game 40, Shaq scored 2 out of 4 attempted free throws. And then in game 41, he scored 5 out of 7, and then 1 out of 3, 4 out of 5. So those are all different success rates, right? And there could be two explanations. They're not necessarily competing, they might be complementary of what's going on here. So one possible explanation is, well, Shaq's underlying scoring rate, meaning if he attempted 1,000 free throws, is the same in all of those games. So if he attempted 1,000, let's say that he'll score around 600 every time. But because he's just attempting 4 and 7 and 3 and 5, the rate naturally would be different just due to kind of dumb luck, not due to difference in skill. The other kind of explanation would be, well, there are bad games and good games for Shaq, right? So sometimes he's doing really well because his underlying skill on that particular day is really good. Other games he's doing poorly because the underlying skill is low on that particular game. So here, maybe in game 42, he genuinely, if he tried 1,000, he'd just score, about 300 as opposed to kind of more. Okay. So that is the question we're trying to answer. Is there is definitely variation in terms of how much he scored. The question is, or kind of the scoring rate rather, the question is that due to good games and bad games, or is that due to just random variation? So here's a picture of the model that we have. So we have different skill levels on different days. It might be that they're all equal, we don't know yet, right? So here you'll have the skill level alpha 1 on game 1, and then skill level alpha 2 during game 2, and so on. And here you'll have skill level alpha 22 during game 22, right? So you want to model those somehow. So maybe what we'll say is that alpha I is normally distributed with mean mu and standard deviation sigma. Okay, so that would be the model. So we'll say, okay, the alphas basically would differ if sigma is large, right? So if sigma is large, you would say, well, maybe alpha 1 would be really small, but on the other hand, alpha 22 might be really large. On the other hand, if sigma is small, then that kind of means that all the alphas are the same. So how do we translate the alphas into actual number of points scored? So what we'll say is that, well, what influences the amount of points scored in free throws from in game 1 is the skill level, but it's also the number of attempts, right? So this would be an attempt 1. Same with score 2, right? So score 2 here would look like this. So this would be score 2. And this would be an attempt 2. Okay, and so on. So here it's going to be the same thing. So here this is scored 22. And this would be an attempt 22. Okay, so how are those related now? So how do we get score 2 from alpha 1 and an attempt? So what you mentioned is that you could actually model that as a binomial. So you could say that scored 1, or in general scored I, that's going to be distributed with a binomial distribution with a probability of scoring that we'll get to in a second, and with the number of attempts being just the number of attempts, right? So we'll say n attempts I, like this. So what should this be? So this should be the probability of scoring on game I, right? So that's the skill level. Now, this could be any number. It doesn't have to be between 0 and 1. It could be negative. It could be very large. Hard to say, right? So what you do generally in this kind of situation is you use the sigmoid function. The sigmoid function takes a real number and it transforms it into a number that's always between 0 and 1. So here we'll just say sigmoid of alpha I, like so. All right, so that's going to be the model. So how is, score 2, for example, generated? Well, the first thing that happens is that alpha 2 is generated. Alpha 2 is the skill level during game 2. Then once you know alpha 2, you have n attempts, so this would be n attempts 2. So you know n attempts 2, so then you say, okay, like on average, you'll score alpha 2 times n attempts 2. But not always, right? So sometimes it would be less, sometimes it would be more. It's governed by the binomial distribution, right? So the binomial distribution will tell you exactly like what's the probability of scoring 1, what's the probability of scoring 2, what's the probability of scoring 3, and so on. And the highest probability is going to be assigned to a number that's close to alpha 2 times number of attempts 2. All right, so that's the model, which kind of in the homework you should write down basically, and kind of in a way that makes clear that you understand it. And that's already coded up in RStan for you. Okay? So what's the next thing that you need to answer? The next thing that you need to answer is, well, based on the posteriors of all the parameters of the model, so the parameters would be mu and sigma, and you're also estimating the latent variables, alpha 1, alpha 2, and so on, are the skill levels different on different games? Or in other words, are there good games and bad games for Shaq? So let's look in a little bit of detail again at what posteriors actually mean. So what you get is a table that's kind of like that. So it has, for example, like 12,000 rows, right? And each column corresponds to samples for the posterior for each one of the variables. So you have samples from the posterior for mu, samples for the posterior for sigma, for alpha, and so on. What do I mean samples from the posterior? Well, once you have a model and you've observed the data, you can try to estimate mu. You would not know mu, for example, exactly, but you would have a probability distribution where the highest probability corresponds to the mu that you believe in the most. So if you plotted this distribution, it wouldn't have to be normal or anything, but it might look, well, maybe something like this. So I tried to make it not symmetric just so that it's like not exactly normal, right? So if you look at those samples, those will be the samples from this posterior distribution, which indicates your degrees of beliefs in the various values of mu, okay? And if you plotted the histogram here, it would look like the posterior distribution for mu, because those are samples from this distribution. So basically this distribution and those samples, they kind of represent the same information. What can you do with this? Well, one thing you could do is you can, for example, take the mean or the median, and that would be your estimate for your best guess for the value of mu, right? Or you could just keep it as a distribution, and you could say, well, like mu is probably around here, but it could also be here, it could also be here. So mu by itself is not that interesting because that's the mean of those alphas, but those alphas, who knows what they really mean, right? So what's more interesting is the sigma. So I'm just making up a distribution for the sigma, and you can get it by looking at kind of the histogram of this, right? So, well, like just making it up, maybe it looks kind of like this. All right. So this says that, well, sigma, the most likely value for sigma is over here, for example. You can take so this would correspond to the mode. You can also take the mean or the median, and you could say, okay, so this is what I think the sigma is. Now, the larger the sigma is, what does it mean in model? It means that the alphas could be further spread apart, right? So if sigma is very large, because the alpha i's is distributed normally with mean mu and standard deviation sigma, right? So if the sigma is very large, then the alphas could be very different from each other. The alphas being very different from each other, that's exactly what corresponds to there being good days, meaning alphas are small, and, sorry, alphas are large for good days, and bad days when alphas are small. Now, your task is to say, okay, well, so this is what I think sigma is, and then to figure out, well, what's a sigma that indicates that there is a practical difference between the alphas that are larger in this model and the alphas that are smaller. So you'd need to think about how to translate that into the language of actually the probability of scoring, and then you'd have to make a judgment call, and I don't really care how exactly you make that judgment call, about what difference in probabilities of scoring counts for a large difference, and what difference in the probabilities of scoring counts as something that kind of practically doesn't make very much of a difference. So for example, if you kind of find that the sigma leads to such a difference in alphas that, you know, at most you'd see a difference between like 50% probability of scoring in one game and 52% probability of scoring in another game, well, like in that case, I would say, well, that's a pretty small sigma, all things considered. It doesn't actually lead us to have good days and bad days. On the other hand, if your sigma is so large that the alphas are so different that the probability of scoring in one game, the underlying probability, right, not the actual measured probability, is like 10%, and on another game it's like 90%, well, that's clearly a large difference. So that's the task. So the next task, once you've like looked at that, is to actually look at the alphas and to plot your estimates for the alphas. So how do you do that? Well, what you can do is you can say, okay, so I have the posterior distribution for the alpha, right? So the posterior distribution, for example, for alpha 1, like whatever, I'm just making up numbers here. So maybe it's like here 0.7, 0.6, 0.7, 0.2, whatever, right? So you can plot a histogram of that. So this is alpha 1, and maybe, you know, maybe it looks something like this, whatever. So if this is the histogram for alpha 1, how do you get the 95% predictive interval for alpha 1? Well, what you need to do is you need to take the interval that covers 95% of the values of alpha in here, or equivalently in this histogram. So it would be like, well, so 95, it would be something like between this and this. Once you have this interval, so you have like the smallest value for alpha and have the largest value for alpha, you can then kind of put it into ggplot in order to nicely plot this interval together with the intervals for all the other alphas. Okay? And it might look similarly to what you see when you plot the confidence intervals as opposed to the predictive intervals, right? For the log radon levels rather in Minnesota.